Okay, coming to teleportation first. Of course, here today I'm talking about quantum teleportation. Coming to teleportation. Usually, those who would have read some books on science fiction or watched a film of science fiction on television would have been familiar with teleportation. What exactly is teleportation? Is a device or a process by which people can jet around the galaxy. Okay. The basic idea is that we get scanned somehow, turned into energy, then beamed to where you want to go and get rematerialized at the place of your choice. Okay. Now, in the realm of science fiction, probably this remains as a thought only, but quantum mechanics allows to do something really most magical. That is, it allows to send a quantum state from one place to another without the state traversing the space in between. Okay, I repeat, quantum mechanics allows to send a quantum state from one place to another without the state traversing the space in between. Okay, how that happens, let us see. Now, entanglement, we have seen in our previous video, quantum entanglement. Of course, quantum entanglement was called as spooky action at distance by Einstein. At distance, he used this word spooky action at distance. Okay, now to see how quantum teleportation works, let us see what exactly we are trying to do is, there is a task at hand, that is Alice wants to send an unknown state to unknown quantum state. If I'm calling in quantum, I know what it is. Okay, unknown quantum state to Bob. Okay, let's denote that state by Ketzai. Okay, we all know what Ketzai is. Okay, there is a psi, there is a xi. Okay, so I'm talking about xi here. All of you are aware of Ketzai as well, psi as well, Ketzai as well. This is a qubit. Okay, Ketzai is a qubit in superposition state. All of you know that it is in superposition state, and of course, this condition is anyways valid. Mod alpha squared plus mod beta squared is equal to 1 by the Bloch-Spear definition, dot dot. Okay. Now, the following are the steps or the working rule. Following are the steps. I'll just put them in short. Following are the steps. Okay, basically what Alice does is, for the other person not to know what exactly she is sending to Bob, what she does is, first she pairs up this Ketzai with an EPR state. Okay, first she entangles this and forms an entangled pair using an EPR state. We have discussed in the previous video what exactly EPR states are. Okay, Einstein, Podolsky, Rosen is the full form. Okay, now entangled pair she forms first. Then exactly what she does is, she applies C0 gate and Hadamard gate and then makes it look like something else, and then finally reveals to Bob some measurement or some code word through classical communication, and Bob decodes it, reveals through classical communication some code. Okay, Bob decodes it and gets back the Ketzai. How this happens, let us see. Okay, let us see how this happens. Okay, first thing is entanglement with the EPR pair. Okay, so we are considering here the EPR pair, this EPR state, I can say, not pair. EPR state I am considering. What is that EPR state here? For example, the EPR state under consideration is beta 0, 0. You are aware of it. It is 0, 0 plus ket 1, 1 by root 2. Okay. Now, what she does is, the first one belongs to Alice, second one, first qubit belongs to Alice, second qubit belongs to Bob, is what they decide prior only. Okay. So, I will notate it like this. Just see, beta 0, 0. I rewrite it like 0A, 0B plus 1A and 1B by root 2. Okay, this is the EPR pair. Clearly, it is obvious. First qubit is Alice. First qubit is Alice, or is instead of using is, belongs to Alice, I will say. Belongs to Alice. And second one belongs to Bob. Okay. Already there is one more which belongs to Alice. Okay, what is that one? Ketzai. Ketzai also belongs to Alice. Okay, so accordingly, let us act. Let's create the entangled pair first with the EPR state. Let's call that with psi. What is that? Ketzai tensor product of the with the EPR pair. So what do I get? Alpha ket 0 plus beta ket 1. Okay. This with 0, 0, 1, 1 by root 2. Tensor product, all of you know. Or if you are not aware, just check my previous videos for the tensor product. You will understand. Okay. Yeah. So what happens is, alpha 3-qubit system is what I will get. 0, 0, 0 plus with alpha ket 0, I will be getting alpha 0, 1, 1. With beta ket 1, I will be getting 1, 0, 0 plus beta triple 1, I will be getting with 1 by root 2. Okay. Now, what's the first step that Alice does is, after entangling it with EPR pair, she applies a C0 gate. Okay. That's step 2. Step 2 is what? Step 1 is entangling with EPR pair. This is step 1. Entangling with EPR pair. Step 2 is applying C0 gate. Alice applies C0 gate. Okay. So how does that happen? Let us see. I'll call that to be Z ket xi prime. Ket xi prime. C0 of ket psi. Okay. So what's it? 1 by root 2. Alpha as a constant can be taken out. Okay. C0 of plus C0 of 0, 1, 1. This is with alpha plus beta C0 of 1, 0, 0 plus beta. Beta is anyways common. Okay, I can enclose it with a bracket. C0 of ket triple 1. Okay. Now, what she does is, the C0 gate she applies on her qubits. Okay. What are this? What are those? I will write here first. Star mark and write here one important point, that is, first two qubits. First two qubits are Alice. Qubits belong to Alice. Belong to Alice. Okay. Last qubit or rightmost one belongs to Bob. Okay, guys. Right. So she applies C0 on her qubits only. Okay. So what happens? Uh, I know about C naught gate. Again, you can check the videos for C naught gate. When control bit is 0, the target bit doesn't change. It is as it is. Okay, as long as the control bit is 0, nothing changes. Once the control bit changes to 1, there is a bit flip. Regarding, I know about C naught gate, guys. We have discussed in our previous video. Do check. Once the control bit is 1, there is a bit flip. What happens? 0 flips to 1. Once the control bit is 1, 1 flips to 0. Okay. So now what happens? Get xi 1 prime would be 1 by root 2 is common for both the terms. With alpha, I have no change. Okay, alpha terms, there is no change. In beta, there is a bit flip because there is a change in the control bit. Okay, so 1 0 becomes 1 1. So that becomes triple 1. Okay. No, not triple 1. Just a second. There's a printing mistake. Yeah. 1 0 becomes 1 1 and the last 0 is as it is plus beta into triple 1, and in that 1 1 has become 1 0. So 1 0 1 it would be. Okay, this is how I will get. Next, what I'll be applying, she'll be applying in step 3. What? Step 3, what she'll be doing? She'll be applying Hadamard gate. Alice applies Hadamard gate. Remember, guys, whenever I'm applying an operator or a gate, always, if one gate is applied, I can do that only on one qubit. If two gates are applied, then it is possible only on 2 qubits. Okay. And then if three qubits, I cannot just apply two gates on 1 qubit kind. Okay. Or one gate on 2 qubits. I can apply only one. See why? Because just see here, if I'm talking about it, if I'm saying I should apply, if I'm applying 2 gates, there should be 2 qubits, right? Why? Because one gate is applied on 1 qubit, other is applied on another. Independent. First on first, second on second. So Alice applies H gate. On what she will apply? Of course, she can apply only on her qubits, right? So let us take the first one. H gate, she applies it on first one. Let us suppose. I know what the property of H gate is. H of 0 would be what? Ket 0 plus ket 1 by root 2. H of 1 would be ket 0 minus ket 1 by root 2. Always remember these notations, guys, with Hadamard gate. Hadamard gate is very important. Of course, XYZ gates, when operated on the computational basis or the basic states, what happens? Always they should be on tips. Only then you can master quantum computing. Okay. Yeah. So ket xi prime, I am rewriting it as alpha ket 0 0 0. Okay, I can just scroll up so that you understand what I am doing. Yeah, I'm splitting because one Hadamard gate, so one ket should be there clearly. Of course, I can take from the first 2 ones. Okay, I can take from the first 2 elements, ket 0 out. Okay, so I'll be having 1 1 here. From this second element, I can take ket 1, the first qubit. So I will have 1 0 plus 0 1. Clear? Right. Now we will apply Hadamard gate. Okay. Let's call this to be xi double prime, which is nothing but h of xi prime. Okay. So alpha h ket 0. There is a by root 2, of course, here. By root 2 and a by root 2 here. Okay. of course I can take 1 by root 2. H is 0. Ket 0 0 plus ket 1 1 by root 2 plus beta H ket 1 1 0 0 1 by root 2. Okay guys? Right. Now what I will do, I will rewrite what is H of ket 0. What's it? Ket 0 plus ket 1 by root 2. And this is 0 0 1 1 by root 2. I know what happens. Root 2 into root 2. Beta ket 0 minus ket 1 by root 2 1 0 0 1 by root 2. Okay, root 2 into root 2 becomes 1. I can take out 1. Root 2 into root 2 becomes 1 by 2. I can take it out. Now just see here. I am left with this such a huge thing. Now the final step that Alice does is she measures her pairs. Okay, what she does is she measures her pairs. What she does, the first two, I'll just use a different color so that you understand. The first two are her pairs in every one. Okay, so what she does, the first two she separates, right? So what happens here, actually by 2 I have taken out. Actually I'll be having something like this. Just see, 0 0 0 plus 0 1 1 plus 1 0 0 plus 1 1 1. I have something like this with alpha. Of course, these are all with alpha. Plus with beta, just see, with beta I have 0 1 0 plus 0 0 1 minus 1 1 0 minus 1 0 1 is what I have with beta. Now what she does is she measures her pairs. So what happens is 1 by 2, she measures her pairs means what? She takes out her pairs. What are those? 0 0 0 1 1 0 1 1, all those she will take out. Now you see, if I take out 0 0, what are the elements that I have in common? If I take out 0 0, I'll be having alpha ket 0 plus alpha ket 1 plus alpha ket 0 plus alpha ket 1 in the first one plus, no, just a second, something wrong. Yeah, if she takes her first two qubits, then what will be there? Just see here. If she takes her first two qubits, then 0 0 will have alpha ket 0, guys. Now where is another 0 0? There is another 0 0 with beta ket 1 I have. Got it? This one and this one. Next, if she takes the next one, 0 1. If he takes her pair, I'll be left with alpha ket 1. Okay. In beta, if I take out 0 1, I'll be left with the plus beta ket 0. Okay. Plus. Next one is, if I take 1 0, the Alice pair 1 0, I'll be left with alpha ket 0. Okay. 1 0 if I take, where is it? 1 0 1 0. Here it is with a negative beta and ket 1. Okay. Plus finally, if I take 1 1, then what happens? Alpha ket 1 is there. Also, there is a negative beta. If I take 1 1, where is 1 1? This one with ket 0. Okay. I'm again telling you, in the fourth step, Alice measures her bit. Okay. What's that? Step 4. Alice measures her qubits. That means what? She takes the measurements in such a way that her qubits are pulled out. What are her qubits? The first two are her qubits. So she pulls out all her qubits first, then sees what terms are in common. Now you see there is one huge get xi double prime. Nothing can be understood to Bob if this is sent as a message. Now what she does in step 5, Alice gives an information in step 5 through classical channel. What can be that channel? Phone, mail, or fax. Through that, she'll give a hint saying she says measure 00. If she says measure 00, if she says measure 00 to Bob. Alice says measure 00 to Bob. Then what Bob does is he applies identity gate to 00 coefficient. Okay, what is identity gate of alpha ket 0, beta ket 1? Identity gate or identity operator gives the same thing. Get psi is what I will get. If Alice says measure get 01 to Bob, then what he does is he applies X gate. Just see here. What is there? Just see here. There is a alpha has to be accompanied with ket 0, but it is with ket 1. Beta is with ket 0. That means there is a state flip or a bit flip. Okay. So what he does is he applies X gate to it. 1, beta, ket 0. He applies X gate, and all of you should have on tips what happens if X is applied to ket 1 and X is applied to ket 0. X is nothing but your NOT gate kind. There is a bit flip. 1 flips to 0, 0 flips to 1. So 1 flips to 0, 0 flips to 1. Hence I will be getting ket xi. Okay. If she says 10, then what Alice does is he goes with Z. What? Just see here. 10. What is the coefficient? State flip is not there. Alpha is with ket 0 only, beta is with ket 1 only, but there is a negative sign. So there is a phase flip. Hence he goes with applying Z gate. Okay, guys. So again, you should know on tips what happens when Z is applied to ket 0 and what happens when ket is applied to Z1. Okay, what happens would be no change in ket 0. This becomes beta ket 1. Okay, this is nothing but my xi. Oh, of course, if she says this, if she says measure ket 1, then what he does is he applies X gate and Z gate, because in this there is a state flip as well as phase flip. Why? Because alpha should be with ket 0, beta should be with ket 1, but it is ulta. At the same time, there is a negative sign. So once X is applied, you know what happens? Okay. What happens when X is applied? There is a bit flip. 1 becomes 0, 0 becomes 1. Okay. Now once Z is applied, there is a phase flip. No change on ket 0. There will be a change on ket 1. Hence, I will be getting ket xi. That's how Alice communicates the code. Use this measurement if she says. See, if no classical communication is used, then the state that is resultant of applying C0 and Hadamard gate will look totally random to Bob. Okay, so she tells her measurement through classical communication, again not revealing anything except for some code state. Okay, this is all about quantum teleportation, guys. It's similar to your cryptography in normal language. Okay, yeah, with this I'll stop this video.